This was actually the last example that we had talked about, was how you can use graph to identify, where your function is, basically where your y values would be positive, negative, or equal to 0. So this was similar to the example that we had done, and then of course you have examples in your handout. That you can kind of look through. So we had also talked about this example last time on how you can use the graph to solve this. And then this one here is talking about using test point method. So can you remind me what the test point method is? We talked about this when we were talking about solving quadratic inequalities. What does a test point method look like when you're trying to solve an inequality? Anybody online? What is the test point method?
Is it where you solve for the zeros and then you take points on like each side of the zeros and then test if they're positive or negative?
Yeah, very nice. Perfect. So that's exactly what the test point method does, is you have to find your roots or your zeros, which is also your x-intercepts basically. So you find your zeros, your roots, and then you put them on a number line, and then we basically try and see what our y value would look like, on each of those intervals. So let's talk about finding the zeros for this example over here. So we have x to the 4th minus 4x squared. So if we had to set this equal to 0 and solve it, where would we begin? So I'll give you guys a couple minutes to think about this. How are you going to solve this equation to find its zeros?
Did you factor out the common?
Okay, start by moving the common factor out, which would be what in this case?
X squared.
X squared, very good. And let me see, I've got something on the chat here. Yeah, Della, very nice. Set it equal to 0 and then factor it out. Perfect, very good. Okay, so let's see what that ends up looking like. Okay, so what are we left inside the parentheses? Very good, x squared minus 4, because you have x to the 4th. So if you're taking 2 of those x's out, you're only left with 2, right? So x squared minus 4. And then what will those zeros look like?
So x squared equals 0 and then x squared minus 4.
All right, perfect, very nice. Take each of the factors, set them equal to 0.
They both have a multiplicity of 2 because it's x squared. So would the one on the right be almost multiplicity of 1?
Well, you will actually see the one on the right kind of breaks down differently, but yeah, the one on the left will have a multiplicity of 0. Sorry, 2. So what does that answer come out to be from the left-hand side?
0.
Good. Because, again, you can kind of do the square root on both sides. But then again, since it's a 0, 0 doesn't take positive or negative signs, so you just end up getting 0 over here. Of course, the square root and the square cancel each other out, and this guy definitely has the multiplicity 2. There's too many i's in there. All right, so multiplicity 2 for x equals 0. Now, what will happen on the right-hand side over here with the x squared minus 4?
Would you get plus or minus?
Yes, that's exactly what happens. So start by moving that 4 to the other side. Of course, this cancels out. And then when you take that square root, this is where you're going to get one positive and one negative root from here. So x from here, and then this is positive or negative 2. The other thing you could have done with this guy is, I'll show it to you down here. Since you have x squared minus 4, it's the same thing if we were to rewrite this as x squared minus 2 squared, right? So give it that difference of squares kind of look. So a squared minus b squared. And remember, when you have difference of squares like these, they factor into x plus 2 and x minus 2. So remember, this is coming from the difference of squares. So if you have a squared minus b squared, it factors into a plus b. A minus b. So that's why you can see they actually each have multiplicity 1, right? So it's not really multiplicity 2 because the x minus 2 is coming from here. The x plus 2 is coming from here. So each one of these guys will have multiplicity 1. So now, once you have found your zeros, this is where we put them on the number line. So that this is just your x-axis basically. And let's see, we had one of the zeros as 0 itself. And then the other zeros were positive 2 and negative 2. So as you can see, since we have 3 numbers in there, we're breaking our number line into 4 sections. So now we have to figure out what the y value will be in each of these. So we need to pick a test point from each of these intervals. So between 0 and 2, we can obviously do 1. After 2, you can pick a 3, just keep it simple, right? Between 0 and negative 2, we can go with negative 1. And then this side again, we can choose negative 3. So those are our test points, right? The numbers that I have here in blue. So now what you do is you take each of the test points and put it into the original polynomial, and then you try and see, is my y value going to be positive or negative? And that's how we know what the sign is going to look like. So let's do our test points. And this one will be x equals negative 3. So that would be negative 3 to the 4th power minus 4 times negative 3 squared. So what will our y value come out looking like here? So Della, to answer your question, the x plus 2 by itself has a multiplicity of 1. And then the x minus 2 also has a multiplicity of 1 because they come from different factors. So each one of them has one multiplicity. Okay. So what did we get for x equals negative 3, guys? So we know negative 3 to the 4th power will become a positive number. Same thing with negative 3 to the 2nd power will become a positive number. So the only negative sign you will have is right here in the middle. And depending on, is this number large enough that, you know, we keep the positive sign is what we're looking at. So what did you guys come up with? 45. So that would be a positive number, right? So that was negative 3 to the 4th power minus 4 times negative 3 squared. Alrighty, so this will be a positive 45. So that means our y values are going to be positive in this interval. Our next test point was x equals -1. So this would again be -1 to the 4th power minus 4 times -1 squared. What will he give us? Yeah, perfect, Bella, very nice. This ends up giving us -3, right? So that's a negative sign, which means our y values are going to be negative in the second interval. What about the positive one?
But it's still -3.
Yeah, it's still going to be -3. Yeah, very nice, Ella. So that tells me third interval is also negative, and then of course, our last test point was x equals +3. So 3 to the 4th power minus 4 times 3 to the 2nd power. What do we get? Hey, Della, very nice. Yeah, 45. So again, it's a positive number, which tells us in this interval, our y value is also going to be positive. So now the question was, basically, when is this polynomial going to have values less than 0, right? So it's the same thing they're saying. Basically, when is the y value less than 0? So which interval would you select for this? Where is our y value less than 0?
Between -1 and 1.
Yeah, so Della, it's not actually going to be a single number, it's actually going to be an interval. So basically, say that again?
Between -1 and 1.
So remember, those were just our test points. The intervals are actually the numbers in the green. Because that's gonna be where our zeros were, right? So you're using your zeros. Because right where your x is equal to -2, +2 or 0, remember that is where your y value is equal to 0. So right here, at this point, y is equal to 0. But we know between -2 and 0, my y value is negative. Between 0 and 2, my y value is also negative. So when you are writing out your solution set, and since this is strictly less than 0, not including 0, you are of course not including your endpoint. So we would be going from -2 to 0, all with parentheses, and then union, pick right up on the other side, so from 0 to 2. Because that is where our y values are negative. Y is positive on the left-hand side, y is positive on the right-hand side. So this graph, if we were to graph this guy, would actually look very similar to that example I was showing you in my math lab. So let's graph this, x to the 4th minus 4x squared. And obviously, this is a much nicer graph than the last example we were looking at in class last time. So over here, you can see this is where our zeros were, -2, 0, +2. And this was a simple enough example that we didn't have to worry about a lot of the techniques that we learned in this section, just because it's a nice, easy example. But you can see all over here, your y values are less than 0. Then you come to 0, stop there, and then you pick right back up after it, and all of this is where your y value is 0, and that's what they were asking us, where is x to the fourth minus 4x squared less than 0, and that's going to be between the interval from -2 to 0, and then from 0 to 2. Questions on this one, guys? Alrighty. So that was basically the last part of section 3.4, just to kind of show you guys how the test point method works. Anybody have questions on this? Anybody online? So Della, yes, it is going to be only the negatives, but like I said, it's going to be all that interval, right? So you have to make sure you're including all the points in that interval. So that's why it was, that -2 to 0 and then 0 to 2. Did anybody else have questions online? No? Yes.
So for less than or equal to, would you have to do the union or no?
So if it was less than equal to, then the only difference would be instead of parentheses, you would have put brackets on the endpoints. Yeah. Very nice. Alrighty, guys, so this was end of 3.4. Let's get into 3.5. So 3.5, we're actually getting into rational functions. So far we've been talking about just polynomials, right? And we were just talking about how to find those zeros. We looked at several different theorems to kind of help us narrow down our answers, and we talked about graphing. Now we're talking about rational functions. So all you really need to think about when you're working with rational functions is basically think about that now both your numerator and denominator can be polynomials. So basically we're talking about taking what we learned about the polynomials and applying that to ratios of polynomial functions. So your examples can obviously look something as simple as y equals 1 divided by x, or you can have something like this, f of x equals 2x minus 3 over x minus 4, and of course it can get more complex from there. So basically when we're talking about a polynomial function versus rational function, we're saying both p and q functions are polynomial. You're setting them up in this rational form, so as a fraction. And the only thing we have to be careful about is the denominator cannot be a zero polynomial because it is still a fraction. We're still writing it as something divided by something else, and division by 0 is still undefined. So remember that denominator function cannot be 0, basically. So they are telling us just to make an assumption that your rational function f of x equals p of x over q of x will be given to us in the lowest forms. So you wouldn't have to reduce it unless they tell us that, reduce your rational function down. So for the most part, we'll assume it's already in the reduced form, but if they tell us to break it down and reduce it, then of course, we can do that. So remember for polynomial functions, we basically said the domain was all real numbers. Well, even though these are polynomial functions, right, put in the rational function format, that is not going to be true here because you have something on the denominator. And as long as you have your x variable in the denominator, you will have some number which will make your denominator 0, which means that is the same number you have to exclude or leave out of your domain. So the domain of your rational function is restricted to real numbers that do not make your denominator a 0. So basically, if you look at that function, we looked at y equals 1 divided by x. Well, my x is in the denominator, right? Which means x cannot equal 0. So since x cannot equal 0, my domain for this function would be all real numbers except 0, right? So the way you would write this guy would be negative infinity to 0 union 0 to infinity because we're leaving the 0 out. On the number line, this guy would look like, positive infinity here, negative here, 0 in the middle. So we're leaving the 0 out, but then everything else is okay. I know you guys thought you were done with domains. No, you're not.
Wait, is that for, that's not for number 1, right?
No, that's just for the 1 over x function. Yeah. So for something like number one, you have x squared minus 9 in the denominator, right? So think of it just like a polynomial that you're trying to find zeros for. And that's where we're going to begin with this guy, is just look at the denominator, set it equal to 0 and solve it like you're finding its zeros. So can you tell me what the solution to x squared minus 9 equals 0 will come out to be?
3 plus or minus 3.
Very nice, perfect. So again, you can factor this or you can use the square root property. If you want to factor this will factor into x plus 3, x minus 3, because again, remember, you can write that 9 as 3 squared. So then these guys will give you x equals -3 and +3. Now remember, that means both of these numbers are going to make our denominator 0, because if I take -3 and plug it in for my x squared, well, -3 times -3 becomes +9. Same thing with +3. If I put 3 times 3 in there, it also becomes 9, and 9 minus 9 will give us 0, right? So that makes our denominator 0. So this is telling us when we're doing our domain, we cannot use -3, we cannot use +3.
Wait, why does it, what is this?
Because that is what makes our denominator into a 0, right? Because that's the calculation we did during our denominator. Yeah, so this is telling us the solutions for the denominator functions are the same numbers that make our whole rational function a 0. So again, you can use every other number except those two. So that means everything in this interval is okay. In that middle interval is okay, and of course the last one. Just don't use 3 and -3 itself. So can you tell me in interval notation what this domain will look like? How will we write it out?
So wouldn't it be 3 of them? Would it be 3 of them?
Yeah, because you have 3 sections. Yeah.
Why would you do -infinity to -8 with no bracket? And then -3 to 3, obviously no brackets again. Yeah, then -3 to +infinity.
Not
Oh, 3 to
Yeah.
+infinity, no brackets.
very nice. Yeah. So literally anything between -infinity and -3 is okay. Then we use the union symbol between -3 and +3, and then from +3 to infinity. So since we are leaving out -3 and +3, you use parentheses on those numbers. Della, yeah, perfect, very nice, very good. And of course, infinity always takes parentheses, right? So there will be no brackets whatsoever in this guy. Alrighty, perfect. Let's see what's our example here. Okay, so kind of similar to what we just talked about. X to the third power minus x is our denominator. And when you're talking about domain, the numerator really does not matter. It's only the denominator that's causing problems. So can you tell me what makes our denominator 0? Yeah, Della, so in this case, because you have -infinity and infinity on either side, so of course we only use parentheses for them. And then since we cannot use -3 or +3 because they make our denominator 0, you put parentheses on them also. So yeah, you don't end up using parentheses, brackets in this case. Okay, awesome. All right, what's making this guy a 0? Would it be 0? I don't know. Let's factor this expression. What do we get? What would be common between x to the third and x?
X
X, yeah, so bring the x out, and what are you left with?
squared minus 1.
X squared minus 1, very nice. So actually very similar to that polynomial we just did. Take each one of these, set it equal to 0. And what will our x values come out to be?
Just 0 and then plus or minus 1. So
Yeah, very nice. So again, you can use square root property, or if you want to use factoring. So you will get x equals -1 and +1, and then of course x equals 0 from here. So this means there are three numbers that you cannot use now, because all three of these numbers are making our denominator 0. So on the number line, let's see, we cannot use 0, +1, and -1. So what will our domain look like here, guys?
So would it be 4?
Yes.
Oh, okay, and then, yeah. Negative infinity to -1, no bracket. -1 to 0, no bracket. 0 to 1, no bracket. And then 1 to positive infinity.
Seriously? Tell me that last one again.
1 to positive infinity.
1 to. Alrighty, so negative infinity to -1, which would of course be this little section here. -1 to 0 would be the second, 0 to 1, and 1 to infinity. Perfect, very nice. Anyone have questions on this one here, guys? Okay. Anybody online have questions on that? No?
Is this a new one? This one on the board now?
Yeah, this is a different type. All right, see, other thing you have to kind of think about when you're working with rational functions is horizontal and vertical asymptotes. Did we talk about vertical asymptotes? My memory is kind of not helping me right now. I don't remember. I have a feeling we talked about it, but I can't remember when. Anyway, we'll talk about it now. So we're looking at the function y = 1/x. Now, if you look at its graph, it actually looks like the graph on the right-hand side. This is just a portion of the graph it's showing you. So what happens over here is, of course, as you can see with 1/x, since x is in the denominator, we cannot have 0 as a part of our domain, right? And we talked about that over here, how you leave the 0 out from this function. So basically what happens is, if you look at your graph, the way it's behaving as it gets closer to x = 0, that's actually right over here, because this y-axis is your x = 0 line. So you will see as my graph is getting closer to the x-axis, it really actually never touches that line. It's not crossing it. It gets close, but it starts heading downward. So what's happening over here is this graph is getting closer and closer to the y-axis, but it's actually never going to touch it, and it's never going to cross it. And that's the same behavior that's happening over here. So that's kind of what they're trying to show you here, is they're saying as your x value is getting closer and closer to 0, your y is actually heading upwards towards positive infinity. And then on the other side, as your x value is getting closer and closer to 0, your y value is actually headed towards negative infinity. So this behavior happens because you almost have like an imaginary line here, which is what we call as the vertical asymptote. And that's what that vertical asymptote does, is the behavior of your graph will be where it gets closer and closer to your line, wherever that vertical asymptote is. And it's going to get closer to it, but it's never going to touch it, and it's definitely never going to cross it. So that's your vertical asymptote. And your vertical asymptote for rational functions are at the same places where you cannot use them in your domain. So for this function over here, this is the same place where you will see the vertical asymptotes on this graph. So at -3 and at +3 for the x value. So honestly, when you're finding your domain, you have also found your vertical asymptote. It's the same calculation that you do. So for that function, we just looked at, and I think I already erased our work. Oh, did I not type in our answers in? So this one was what, -1, 0, and +1 we couldn't use? So
Yeah.
negative infinity, -1. Union, we went from -1 to 0. From 0 to 1. And then from 1 to infinity. So for this function, like I was saying, your vertical asymptotes are going to be at x equals -1, x equals 0, and x equals 1. So the same places where our domain cuts off is the same places where you have your vertical asymptotes. Okay, so that's one type of asymptotes that we have to worry about when we're working with rational functions, but of course, as you can see, we also have horizontal asymptotes. And again, this is a great example because it displays both of them. So you will see as we are actually getting closer to the x-axis, in this case, the horizontal line, same things happening over here. Our graph is going to get really, really close to the x-axis on this side. But again, it's not going to touch the x-axis, it's not going to cross it. So you also have, basically the idea in this case would be as we're getting closer and closer to y, your x is actually headed to -infinity on this side. And on the right-hand side, as you're getting closer and closer to y, your x is headed to +infinity. And you can kind of see in this paragraph, they're talking about the domain for this function was all real numbers except 0. You can see the interval notation here. However, they're saying 0 is important because of the way it behaves. So as you're getting closer to 0, y gets further and further away from 0, right? Because that's where we saw it going towards positive and negative infinity. So that's kind of what they're laying it out here in this little paragraph. They're also showing it to you in a table form here. So you can see as you're coming from the negative side and you get closer and closer to 0 coming from the negative side, look at your y values. They're starting to head towards -infinity. So basically here, x is getting closer to 0. And here your y is getting closer to -infinity. And then on this side, of course, there's nothing defined. So this is undefined over here. And then coming from the right-hand side, as x is coming to 0 from the right-hand side, look at your y values. They're headed towards +infinity. So here's another notation I'm going to introduce to you guys. Since we're coming closer to 0 from the negative side, you actually write it like this. So we know we're coming to 0 from the negative side, and this guy, we're coming to 0 from the positive side. So we give it like a little superscript. And we put it that way, so you know what direction you were headed to on 0. So that's a calculus notation again, guys. So basically, that's where your vertical asymptote happens at that vertical line, x equals 0. Now, this little paragraph over here is talking about the horizontal asymptote. So this is where, as your y is getting closer to 0, your x is moving away from 0, because remember, that is where we're starting to head towards positive and -infinity on the horizontal asymptote. So that's going to be the horizontal asymptote at the x-axis, which as an equation would be y equals 0. And so here you can see as we are getting closer to the y value coming from the negative side, our x is headed to -infinity. As we are getting closer to the 0 on the y-axis from the positive side, your x is headed to positive infinity. This is an odd function, y equals 1 over x, so they're saying this also has symmetry about the origin. And you can see that in that graph on the right-hand side. If you take the distance from the origin. So, and I'm just gonna pick the easiest point. If you take this distance going this way and this distance, that would be the same. So that's how you're kind of looking at symmetry with the origin in that case. So basically, guys, when you're trying to find vertical asymptotes, it's really straightforward. Take a denominator of the rational function, set it equal to 0, and you will find what your vertical asymptote is. However, when it comes to finding the horizontal asymptote, we have to fall back on algebra to help us out. So we're basically saying when you're trying to find your horizontal asymptote, it is determined by what value is your expression approaching as your x is getting closer to positive or negative infinity. So the idea is if I were to take my x values in my rational expression, and imagine what would happen if I make my x go closer to positive infinity or make my x go closer to negative infinity. What number would my function be approaching? And that value is what becomes the horizontal asymptote. So you've got your definition over here, but let's talk about how to actually use this idea to find the horizontal asymptote. So we're going to look at expressions like, you can see all of these examples have a constant number on the top. So you have 500, -3, 5, or 2 on the numerator. But then you have something with x on the denominator, right? So there's no x on the numerator, the x is only on the denominator. So you have integers on the numerator, x values on the denominator, so 500 over x, -3x squared, 5 over x to the third, 2 over x minus 5. When you have expressions like this, what do you think will happen as our x gets closer and closer to either positive or negative infinity? So here's a thing I want you to try. Well, let's take that first example, 500 over x, and keep increasing your denominator. So start by putting this on your calculator. What will happen when you take 500 divided by 999? What answer do you get? Then increase that, make it 9,999. So keep increasing that denominator. And that's us pretending like x is getting closer to infinity, right? So 500 over 99,999, and of course, keep taking it forward. What do you think will happen as we keep increasing our denominator?
Keep getting smaller.
Sorry? Keep getting smaller. What number do you think it's approaching? 0. Okay, let's see what this guy tells us. So we've got 500. There we go, a little bit better. So 500 divided by 999, you can see it's just shy, a little over 0.5, right? So it's slightly larger than 0.5. Okay. 500 divided by 4 of them 9s. You can see it became a decimal smaller, right? So 0.05. 500 divided by 1, 2, 3, 4, 5. 2 decimal places, 2 zeros after the decimal place. 500 divided by 1, 2, 3, 4, 5, 6. Scientific notation. So basically, when it's 10 to the -4th power, do you know what happens with scientific notation? Where do we move our decimal? when it's 10 to the negative 4?
For the left.
Yeah, 4 to the left.
Very nice. Yeah, 1, 2, 3, 4, which means before the 5, you're going to have 3 zeros, right? So basically that's what's happening. So yeah, exactly like you guys said. Because my numerator doesn't change, right? It's that static number, it stays the same. As I keep changing my denominator, I am getting closer and closer to 0. Now you can try this even with negative numbers. So a bunch of zeros, where's my negatives?
No, how many there? Interesting.
We'll see what it does. So basically, it's just approaching 0 from the negative side, right? And so that's what's happening. So that's the thing that's going to happen with each one of these equations over, expressions over here, is as your x gets really, really large, all of these polynomials are going to start getting closer to 0. So as x goes to positive or negative infinity, for that matter, it's not going to make a difference. All of these expressions are going to be heading close to 0. But then when you have something like this expression here, x minus 2 over 2x minus 3. Now this guy has both x on the numerator and denominator, right? So this is going to behave a little bit differently. So for these kind of expressions, what we do is start dividing by the highest power of our x, which in this case, that is x to the first power, because that's the same thing I have in my numerator and denominator. Yeah, Della, that's exactly right. So you're just going to keep seeing those extra zeros show up after your decimal place. And that's how we know that expressions like the 500 over x are always going to get closer to 0. But then when we put both x on the numerator and denominator, it changes a little bit. So you will see we're taking each expression or each term in our expression and we're dividing it by the highest power of x. So you're taking x divided by x minus 2 divided by x, then on the denominator 2x divided by x, and then 3 divided by x. So literally take each term of your expression divided by the highest power of your x value. And then here you will see x divided by x will basically end up giving us 1. Minus 2 over x will stay as it is. Then on the denominator, 2x divided by x, again, your x values will cancel out, leaving us just with the 2. And then the plus 3 over x will stay the same. Now, here's what's going to happen. As my x gets closer to positive or negative infinity, so as my x gets closer to positive or negative infinity, this expression here, he's the same as these guys on the top, right? So he starts getting closer to 0. Same thing's going to happen with 3 over x. He is going to start getting closer to 0. So those expressions will actually end up becoming zeros, just leaving you with 1 minus 0 divided by 2 plus 0, which of course then simplifies to 1/2. So the horizontal asymptote for this expression
How did you get how'd you get 0?
because again, what happens is your x is going closer to positive or negative infinity, right?
Oh,
So it's gonna go to 0.
plug in 0 for x then? Is that what you did?
No, I didn't plug in 0 for x. I'm plugging in 0 for the whole
The whole
expression
-2
over x and the 3 over x, yeah.
Okay.
Because remember, x is what we're treating as going to positive or negative infinity, right? So x itself is getting really large, but the whole expression is going towards 0. So this is actually the technique you have to use when you are trying to find horizontal asymptotes. So you actually have to look at what type of expression do I have? Do I have just a number on the top and x only on the bottom? Then I know by default those expressions will be going to 0 as my x gets really large on positive or negative side. But if I have x both on the numerator and denominator, well, then how do I treat that? What about something like this guy, where I have x on the numerator, but x squared on the denominator? How is that going to behave? So that might be a little bit different. So let's take a look at this guy. So he's actually the same expression. Oh, like 100 years ago. That we talked about from example 1. So it's the same one. So since we already did the calculation for domain, and we know for the domain we cannot use -3 and +3, that's the same place where our vertical asymptotes are going to be. I'm not going to repeat that calculation. Oh, where are you?
How do you know if it's a horizontal or a vertical?
Because the vertical only comes from looking at the denominator. For the horizontal, you have to look at the entire
Oh, the
expression.
vertical is the one we did earlier.
Yeah.
Where we have to equal out to 0.
Yeah, so you just take your denominator, set it equal to 0. This came out as ±3, so our vertical asymptotes were at x equals 3 and x equals -3. Okay, so only the denominator when you guys are working with the vertical asymptotes. Now for the horizontal, and again, this was something. Okay, so remember, you are taking each expression and dividing it by the highest degree or the highest power of x. In this case, our highest power of x is going to be x squared. So you're taking each term, dividing it by x squared. So that's x divided by x squared minus 1 divided by x squared. This was just the numerator. Then on the denominator, x squared divided by x squared minus 9 divided by x squared. So clean this up. When you do x divided by x squared, what do we get?
X.
Where?
No.
In the denominator. So actually you get 1 over x from this guy. Minus 1 over x squared will stay as it is.
So
Denominator?
it should be 1 over x. No, it would be x. Just x, because x squared over x squared is just x. Or is that 0?
That's right.
Come on.
You can't use that?
It's the same thing, right? X squared divided by x squared. It's like 2 divided by 2.
Yeah.
It would be 1, yeah. So this is kind of what it will sort of clean up into. Now, again, we have to imagine what is it going to do as my x gets really large or really small, as it goes to positive or negative infinity, what is it going to do? So remember, as my x is going to either positive negative infinity. That's still there? Okay. As your x is going to positive and negative infinity, remember this expression will be going to 0, right? Because again, I have 1 on the top, x on the bottom. This expression, same thing. He will be going towards 0. And the same thing over here.
The only one that stays is the 1.
Yeah, because it didn't have an x in there that we had to worry about. So when you clean this up, you're looking at 0 minus 0 on the top, 1 minus 0 on the bottom. So our horizontal asymptote is going to be at the x-axis at y equals 0. Questions?
You used x squared because there's x squared at the bottom.
You have to always divide by the largest x
Highest, okay.
power, yeah. So if you look at this one here, you're always dividing by the highest power of x. Della, are you talking about where we're dividing 0 by 1? Because when you're doing 0 divided by 1, you're actually going to get 0 because 0 divided by anything is 0. And I would say just throw that into your calculator and you'll get the same answer, right? Okay, did anybody else have questions there, guys? Oh, where's my pen? Oh, you switched it. Okay, got it. Alrighty. Let's see, what do we have here? Oh. Okay, so this one is talking about determine the equations of all asymptotes for the graph of the function. So we have 2 on the numerator divided by x squared plus 2x minus 15. So let's talk about the vertical asymptote first. So here, remember, just take the denominator and solve that, set it equal to 0 and solve it. So what will we end up getting for this side? X squared plus 2x plus 15.
Mine's
Negative.
Okay, go ahead.
X plus 5 and then it's minus 3.
So what was the negative on?
Negative 3.
Negative. Yeah, very good. So -3 multiplied into +5 will give us -15. And then when we add -3 and +5, we'll of course get +2. So these guys will end up giving us x equals 3 from here. X equals -5 from here. So even though they did ask us about the domain, just to give you guys little extra practice, I guess. Let's see, we cannot use -5. We cannot use +3, everything else is okay. So you can use this, you can use this, you can use this. So what will our domain look like here, guys?
Negative infinity.
Okay,
-5 to 3.
very good, perfect. And then, of course, those are the same numbers where we have our vertical asymptote. So let's see, that would be x equals 3. X equals -5. So those two. And they're asking us to find all the asymptotes. So that, of course, also includes horizontal. And we haven't talked about oblique asymptotes, but we will here in a minute. But let's do the horizontal next. So looking at the type of expression it is, what do you think are horizontal asymptotes would be? And Della, those answers look good, very nice. You have 2 on the top and then your x squared plus 2x minus 15 on the bottom. What kind of horizontal asymptote will we have here?
0.
0, yeah, because as x goes to positive or negative infinity, your y will go to 0 because again, you have 2 on the top and all the x values are on the bottom. So this will go to 0. As x goes to positive. This is actually honestly the same as having that 500 over x, because you just had a integer on the top and all the x was on the bottom, and that's the same thing. What this guy has, you have a static number on the top and your x is on the bottom, so your y equals 0. Is going to be the horizontal asymptote, which is going to be like.
I think it just says your word.
It is in lowest terms, it cannot be put into lowest terms, and the particle asymptote calculating to each root, which is what we have, x equals -5, x equals 3, is there anything else I'm missing there? X equals 15. Because you have 200, okay, let's try this. Which I don't think is gonna make a difference, but if we take each expression divided by the largest x square value. This guy will be going to 0. This guy will end up becoming 1. You have x on the top, 1x on the bottom, so he still ends up going to 0. He's going to 0. So we still end up with 0 over 1. It would still be 0. X plus 3, x minus 3. Yeah, it's gotta be x minus 3, it's gotta be x plus 5.
It doesn't, I don't think it wants you to find the vertical or the horizontal. I think
It doesn't want me to find
Yeah, I think it's
Oh,
Yeah, it's just
okay.
asking for all the vertical.
vertical, so which one do I pick out? This guy?
Yeah, that's it. Yeah, it
Huh,
would be 3 and
interesting.
5. 3 negative 5.
Thank you.
Yeah.
Okay.
No, who's gonna ask me for them? Horizontal. Yeah.
Interesting. Okay, I believe that one is y equals 0. This is very interesting. Okay, apparently it's in 2 parts. So the other type of asymptote we have is, like I said, an oblique asymptote, but usually you will either have the horizontal or the oblique. They cannot occur at the same time. Now, obviously, we can have horizontal and vertical, or we can have oblique and vertical at the same time, but you cannot have horizontal and oblique at the same time. So here's actually a nice little tip they have over here. They're telling us if the degree of the numerator of your rational function is less than the degree of the denominator. So if the degree of the numerator is less than the degree of the denominator, y equals 0, or the x-axis is always going to be your horizontal asymptote. So y equals 0 will always be if the degree of the numerator is less than the denominator. Now, if the degree of the numerator is equal to the degree of the denominator, the x-axis is not going to be a horizontal asymptote, but it's actually going to be the coefficients of your x coordinates. So when the degree of your numerator is same as the degree of your denominator, it's going to be the coefficients of your x value. So that was the 1 and the 2, so 1 divided by 2. And that's exactly what we ended up getting. So again, if the degree of the numerator is less than the degree of the denominator, so those were these 500 over x, 5 over x to the third functions, they were all horizontal asymptote at y equals 0 at the x-axis. When the degree is the same, it's going to be, like I said, the coefficient of your x term, so 1 divided by 2. This example over here, example 2, again, the degree of your numerator was less than the degree of your denominator. So again, x-axis y equals 0 is what we ended up getting as our horizontal asymptote. Your oblique happens when the numerator has a higher degree than the denominator. So if your, does it say that here? Not really. So remember, your oblique asymptote is also a slant asymptote. So it's actually going to be, kind of that imaginary oblique line that's going to happen. So in this case, they're again talking about finding all the asymptotes. So for your vertical, you start by taking the denominator only, set it equal to 0. So as you can imagine, this guy will come out to be x equals 1. If you were to do the domain of this function, everything except 1 is okay. So what would that domain look like? Sorry?
Negative infinity to 1, or yeah, to 1, and then union 1 to
Very good. So the only number you're not using is 1, everything else is going to be okay. So Della, I actually just realized in your answer for that factoring, it should have been x minus 3 and x plus 5. So that's why your x comes out to be positive 3. And the other one was negative 5. So you actually had your sign switched around. Yeah. Okay, very good. All right, so that's our vertical asymptote. For the horizontal, we'll use the same technique that we know, take your highest degree divided into each term. So that comes out to be 3x squared divided by x squared minus 4 divided by x squared, x divided by x squared minus 1 divided by x squared. So on that first one, the x squared and x squared will cancel each other out. One of the x's will cancel out with 1 on the bottom. That's about it. So for the first term, we're left behind with 3 minus 4 over x squared. On the bottom, we're left with 1 minus 1 over x squared. Does that seem right? X squares cancel out, we're left with 3 minus 4 over x squared. Oh, I knew I was missing something. This was 1 over x. 1 divided by x here, and then 1x squared. So as you can see, as your x would go towards positive or negative infinity, this guy over here would be going to 0. He would be going to 0, and he would also be going to 0. So you would be left behind with 3 minus 0 on the top, 0 minus 0 on the bottom, which would be 3 divided by 0. Just add the 1. So you can see no horizontal asymptote. And this is going to happen anytime the degree of your numerator is larger than the degree of your denominator. So no horizontal asymptote, which means we are then looking at oblique. Now you will see for oblique asymptote, they are telling us you will either use long division or you can use synthetic division. And as we saw, synthetic division works a lot better. So let's use synthetic division over here. Okay, so you are dividing by x minus one. Which again, we know when we set it equal to 0 becomes x equals 1, so technically we're dividing by 1. And then from our polynomial here, you are missing an x term, so we should have the 0x for that missing term, so that will be a coefficient of 3. Our missing term 0, and then the minus 4.
Wait, how'd you put, did you just start with one? Just start with one?
No, that's what my denominator is.
Also, you always use what your denominators?
Yeah, because you're dividing the numerator by the denominator, right?
Oh, yeah.
Yeah.
But you wouldn't put a negative one, right?
No, because when you simplify it, you get x equals positive 1. Because
Yeah,
it's
that
x minus 1, right?
No, that makes,
Yeah.
no, yeah.
Now, if you had x plus 1 on the bottom, then of course that would become a minus 1.
Yeah.
So you're literally letting the information help you out. Let me see what you've got here. Yeah, exactly, Della. You cannot divide by 0. So we do have that 3 left behind. But since our denominator became 0, we basically cannot divide by 0. So that's why you can see why we have no horizontal asymptote. Now, what do you get when you solve this synthetic division here, guys?
But you add or subtract? During like the middle, the numbers, do you add down or do you subtract? down?
Depends on the sign. So remember, you're just bringing the 3 down as it is,
Yeah, yeah,
then you're multiplying, right? So 3 times 1 would be 3, and since both are positive here, well, 0 can be anything, but you do end up adding in this case. Now, if you have a negative sign like that minus 4 will have, then of course you'll have to use the sign to tell you. So 0 plus 3 will give us 3. So again, you do 3 times 1, which will be 3. And now, like I said, since you have a negative in there, you end up subtracting, which will give us negative 1. So remember, this becomes part of the quotient. This, of course, is the remainder. So. Trying to remember, I'm having such a memory thing right now. How do we write our oblique asymptote?
an equation.
Okay, so they're telling us we write it as quotient. Now remember, if your original function is an x squared, that means your quotient will be 1 degree less than that. So your quotient will then come out to be 3x plus 3. So this will become 3x plus 3, and then they're saying add the remainder over the divisor. So that would be a -1 over x minus 2. So I'm actually going with this. Use the division to rewrite the function as quotient plus remainder divided by the divisor.
How did you got x minus 1 at the bottom and the negative 1?
Because that's my divisor, that's what I divided by.
Oh, no.
So from the original denominator. So just some terminology to get comfortable with what your dividend is, what your divisor is, what your quotient is, what your remainder is. So anything that you are dividing by is your divisor. What you are dividing is the dividend, because that's the one that's getting broken apart. So remember, guys, the only time you're going to have an oblique asymptote is when the degree of your numerator is larger than the degree of your denominator. And then this little table over here, or box, whatever you want to call it, is listing all the 3 different ways that you can calculate your asymptotes. All right, let's take a look at an example here. So this one is asking us to find vertical, horizontal, or oblique asymptote. F of x equals 2x plus 5 divided by x minus 1. Della, I'm guessing you're talking about the synthetic division we just did, right? Yeah. So in synthetic division, you are multiplying when you have the number on the bottom row with the number that you're dividing by. So in this case, yeah, we did take 3 and multiply it with 1 over here, which is what gave us the 3 here. But then here you are adding these numbers. So we added 0 plus 3 to get the 3 down here. Then you're again multiplying this 3 with 1, which gave us this guy over here. And then since this one had a -4 and a +3, we ended up subtracting to get the -1 there. Oh, for the answer. So for the answer, it's actually going to be in the format of y equals quotient plus remainder over the divisor. So my quotient was 3x plus 3, that's where I'm getting this guy from. Then we take our remainder of -1, which you can either write it the way I did, or you can write this as 3x plus 3, then you can put a positive sign here. And then you can do -1 over, and then the x minus 1, as Luis was asking, is coming from here, what your original divisor was. So you can write it like this, or you can write it as 3x plus 3, put a minus here, and then 1 over x minus 1. Okay, very good. All right, what's our vertical asymptote for this guy? As an equation? All righty, so you are given x minus 1 on your denominator. So when you set it equal to 0, you'll get x equals 1. So just make sure you're always writing this as an equation here, guys. So x equals 1. Okay, so can you tell me if this guy will have a vertical or horizontal asymptote? You have 2x plus 5 divided by x minus 1.
There would be.
Horizontal or oblique?
Horizontal.
Horizontal, because the degree on the numerator is same as the degree on the denominator, so you are actually going to have a horizontal asymptote, not an oblique. So, go ahead.
There can't be an oblique asymptote and a horizontal in the same one.
No,
So if there's a horizontal, I mean, there's no oblique.
exactly. Yeah, very good. So again, since they have the same degree, x on the top, x on the bottom, you'll take each expression, each term, divided by that x. So of course you can see x over x will cancel out, leaving us behind with 2 from the first term, plus 5 over x from the second term. This guy just becomes a 1. So 1 minus 1 over x. So as x goes to infinity, what does our horizontal asymptote comes out to be? Nope. Because this is the same degree, 0 will not be the horizontal asymptote.
2. Y equals 2.
Yeah, very good. Della, yeah, it's gonna be y. Very nice.
Y.
So yeah, because remember these guys, as x is going to positive, negative, infinity, this guy is going to 0. This guy is going to 0. So that basically leaves us with 2 divided by 1, which comes out to be 2. So your y is actually headed to 2. So horizontal asymptote would be at the equation y equals 2. And then when it asks you for the oblique, you will of course say there is no oblique asymptote. Questions, guys?
It just had like an X in the bottom.
So no X on the numerator?
No, so it's like, so when you're doing the oblique, right? So it's like an X squared minus 5x plus 4, but it just has an X on the bottom. What would you put on the side of the synthetic division? Would you
Good
put zero?
question. What will it be? Because X would equal what?
Zero.
Yeah.
So you would put 0 on the side.
Uh-huh. Yeah, and that is one of the examples in your homework. Hey, let's see what kind of asymptotes this guy has. So, Della, you know it's going to be undefined when, your numerator has a larger degree for the X value than the denominator. So like if you had X squared on the top, but X on the bottom, or like maybe X to the third on the top, but X on the bottom. Or you can do what we did in the previous example, which is where we divided, all of our terms in the expression by the largest degree. And then you saw how we had ended up with 0 and 0 on the bottom in this example. So like right over here, where you ended up with both zeros. So that's when you know when your denominator will end up with zeros, it's going to be undefined. And that only happens when the degree of your numerator is larger than the degree of your denominator. Okay. So what's our vertical, horizontal, or oblique asymptote in this example here? Yeah, Della, very nice, very good. So what do we do for the vertical?
Wouldn't it be an oblique? Wouldn't it be an oblique asymptote? Because there's a X squared in the numerator.
Very good.
So the vertical would be -4.
Yeah, so remember, vertical still comes from that denominator. So take the denominator, set it equal to 0. So that would be this guy over here, X equals -4. So like Jen was saying, since we have a larger degree on the numerator than the denominator, you are not going to have any horizontal asymptote in this case. So that y equals is actually going to be coming from the oblique. So again here, since your denominator turns into X equals -4, you are dividing by -4 when you do the oblique asymptote with the synthetic division. So you can see we've got the X squared, we've got the X term. What we're missing is a constant term. So again, we'll put that 0 as a placeholder for it. So for the leading coefficient, I have -1. For the middle term, I have +3. And then for my missing term, which is going to put a 0. So what does our quotient and remainder come out to be in this case, guys?
-1.
Okay,
And then 7.
7 here.
And then -28 is the remainder.
Alrighty, let's check that. So you're bringing the -1 down as it is. Negative times negative becomes positive. So +4, add that together, which gives us the 7. 7 times -4 is -28. So perfect. This is our remainder. This will be part of our quotient. Since my original was an X squared, our quotient will be an X, so that will be -X plus 7. I'm still not sure about how to write this out, but I guess my math lab will tell us if we're right or not. So start with your quotient, negative x plus 7. Then you add your remainder over the original divisor, which would be x plus 4. Or you can write it as negative x plus 7 minus over here, and then just 28 over x plus 4.
It doesn't ask for the remainder.
So that's kind of where I was getting confused, because I was thinking you should only have the quotient.
Because I was putting in the remainder and it kept saying it was wrong.
It kept saying it's wrong,
And then the answer just came out to,
negative x plus 7.
yeah, or y equals negative x plus 7.
Okay, so let's try just with the quotient part. And we'll see what this guy says. Okay. So for the oblique asymptote, then we're just using the quotient. Yeah, so no remainder. So basically what's happening is when you rewrite it in this format, you are actually just rewriting the original expression when you do it with the plus remainder over divisor. So for the oblique asymptote, we only need the quotient part. You don't need the rest of it. And that's kind of where I was getting a little confused of do you include that or not. So yeah, just the quotient, Della, for your oblique asymptote. Okay, so this question is actually just on horizontal asymptote. And again, they're giving it to you in that limit format. But as you can see, they're asking you basically what will be the value of your expression as x goes to positive infinity. So what do you think the value of this expression will be as x goes to positive infinity? Since you have 3 divided by x squared. So as your x gets closer and closer to infinity, what will the entire expression get closer to?
0.
0. Because remember again, when the degree of the numerator is smaller than the degree of the denominator, y equals 0 or the x-axis is your horizontal asymptote. So this is a question on horizontal asymptote, which would be at y equals 0, or in this case, you just put 0 there. Alrighty. I think we should have enough time to get through this. So this one, as you can see, we're now talking about how to graph these rational functions. So some of the techniques will still be very similar to what we talked about in the previous section. So the only new thing we'll be bringing in is, of course, asymptotes, because they make a difference on, where your graph can go and cannot go. And then symmetry always helps out. So you will see in the instructions over here, they're basically saying, make sure your rational function is in lowest terms. So some of them may not be in lowest terms. So far, we've assumed they were, but that's not always going to be true. Talk about what the asymptotes will be. And since they are imaginary lines, they're talking about drawing them as dashed lines. which we were not really graphing by hand, but if we were, that's what we would do. We would talk about symmetry, find any X or Y intercepts if there are. And then, it always helps to have a few additional points when you're trying to graph some of these functions that we're not really sure what the shape would look like. And then, of course, you draw your points through those. So this is again the same example we did in number 1 and number 2. You have X minus 1, X squared minus 9. So remember your vertical asymptotes were at X equals positive and negative 3. That's coming from the denominator. We had a horizontal asymptote for this guy. And again, you will see our numerator degree is small, less than the degree of our denominator. So the x-axis, y equals 0 is going to be our horizontal asymptote. So if we were going to draw this graph by hand, at positive 3, we would have vertical asymptotes. So that's our, dashed dotted line. At negative 3, we have the vertical asymptote again, and then at the x-axis, you also had a horizontal asymptote. So those would be all the lines that would affect. And then this is kind of where we would get into symmetry, which this guy really doesn't have any symmetry. You can see my numerator is neither, my denominator is actually even. But again, there would really be no symmetry in this case. So the only thing you could then do is find X and Y intercepts, use that to graph in this case. So when you're trying to find your X and Y intercepts for equations like these, we would of course make our Y value 0 to find the X intercepts. So finding the X intercepts in this case, make your Y value 0. And as you will see, guys, to even get anywhere to solving this, we would need to take our denominator and multiply it on both sides, which will actually get rid of that denominator completely. 0 multiplied by anything is 0. So X equals 1, yeah. So this would be our x-intercept, which would be right over here. To find the y-intercept, of course, we would make our x value 0. So let's see, that would be 0 minus 1, 0 minus 9. Positive 1, which has a decimal. What is that? Is it 0.11111? Yeah. So 0.11111. Like a hair away from the x-axis, right? So that's all you would be able to gather from this. So as you can see, we're going to need a lot of points to graph this, right? So we would need to know what the points basically on each side. So what would be the points on this side, in the middle, on the right-hand side? What would all of that end up looking like? Okay, so we had x minus 1 on the top divided by x squared minus 9. Oh. So you can kind of see some of those. We do have our x-intercept at 1, 0. We have our y-intercept at 0.11111. Now, this is an interesting thing, and the reason why I wanted to show you, we talked about how at the horizontal asymptote, your graph is not supposed to touch or cross the horizontal asymptote, but the way this equation is, or the function looks like, you are seeing that happen here on the left-hand side. So as my x is going to negative infinity, you can see my y is getting closer to 0. On the right-hand side, as x is going to positive infinity, again, y is getting closer to 0. So at this end, we're definitely seeing that asymptote behavior. at x equals +3, x equals -3, same thing's happening, right? As my x values are getting closer to -3 or +3 from either side, my y value is of course headed up to +infinity or -infinity. So that's happening with the exception of right over here where your where your graph crosses the x-axis and it does have that x-intercept at 1, 0. So every now and then, depending on the function, you can actually have your graph cross the x-axis and end up with an x-intercept, but you're still noticing that horizontal asymptote behavior happening on the right and left side of the graph. So it's, kind of one of those things where you're seeing both behaviors. So what you guys will be doing is obviously not sketching your own graph. Is probably going to give you an option of choosing, but we'll do this example next time. So we're pretty much at the end of 3.5 here, guys. I don't think we have a whole lot of examples left. These are all on graphing. And then rational inequality. So we'll basically wrap this up. Next class, what is today, Thursday? So Tuesday, so next Thursday, which will be what? The 3rd exam day for chapter 3, okay? So please work on your homework. If you need any extra help, let me know. Don't wait till the last minute. So 1 week from today, okay, chapter 3 exam. All right, guys, have a wonderful weekend. Stay safe, everyone, and I will see you on Tuesday. Bye, Della. Take care.